So I think I should begin the open problem session, which will not be the same as they have been. And what I'm going to do is I'll start with 3 open problems that I've prepared. And you'll see 2 of them are old, only one of them's new. And then I'll bring up the whiteboard, which I've never used, but it seems pretty simple. And people can pose problems and either type or draw on the whiteboard. So that's the plan. I'm going to share my screen and show you these problems. Let's see. Okay, so here I'm going to show you 3 open problems. As I said, 2 of them are old. This is an old one. It's known that on a convex polyhedron, there are at least 3 simple closed quasi-geodesics. These are like geodesics, except they can go through vertices. And I worked on this quite a long time ago, 30 years ago, with a student, Stacia Wyman, who is now a biochemistry PhD. And we could not make much progress. But recently, Eric and John Hesterberg and Ku found closed quasi-geodesics, but they are not necessarily simple. So this is now an old problem, but maybe newly rejuvenated by Eric's result. And Eric, if you're here, do you want to say anything about this?
The talk is online on YouTube if you want to watch it, see how it works, but the technique is very much not geared towards finding simple ones.
Yes.
It guarantees finding one, but there's no
it
reason
does
to
not
believe
seem
it would
like
find a simple one.
Right, it doesn't seem like there's a modification of your technique that will lead to simple.
Right.
Yeah, so that's a nice old one.
Quick question, Joe?
Yeah, please.
For the quasi-geodesics, when you go into a vertex, you have to come out in the direction that splits the angles or something.
Close to that, but not quite that. The definition is that you have to come out at an angle such that you have at most pi surface area to the left and at most pi surface area to the right.
Oh, so you have some choices.
So you have choice, yes.
I see. Okay, thanks.
And the proof that there exists at least 3 is non-constructive. So, so this seems to be a hard problem. If I can tell a little anecdote, I mentioned this problem at NYU seminar when Mikhail Gromov was in the audience. And he said, oh, this is easy, essentially, in the discussion. And then he left, and I never got to ask him how it was easy. So all I can say is Gromov thinks it's polynomial. Here's an old problem that I think originates from Leo Gabus. Maybe somebody can correct me, but suppose you have a polyhedron sitting on the plane and you're given a point somewhere else on the plane. Can you roll the polyhedron over edges so that you land on top of the point? But with the condition that every roll vector, and here it's red, has a positive dot product with the vertical. In other words, you're always rolling northward. And the question is, will you land on top of this given point? And I worked on this, and the reason I'm re-raising it, I'm not sure it's ever been solved in a careful computational complexity model where you care about the bits, for example, which incidentally is one of the emphases of this Eric's paper. So does anyone recall this? I'm not sure if this has been solved, but I don't think it's ever been studied carefully. And you can imagine, don't think of the dodecahedron. This is just a little illustration, but just a random polyhedron. There'd be numerical issues in rolling this out to see if you can land on top of P. Has anyone Know anything about this problem? Okay, so that's another.
If Joe, if it is a regular polyhedron, maybe in that case one could have an answer, or a polyhedron that can realize the tiling of the space.
Oh yes, yes. Yeah. It would be relatively easy for an icosahedron, for example. Even a dodecahedron, there. Well, I think that it would be quite possible. Yeah, the real issue is when you just have a random polyhedron. And then you would run into numerical issues because you might have to roll it 100 million rolls to decide, and P might be right on the edge of the northward possibilities. Okay, should I move on? Anyone, any other comment? Okay, so here's a new problem, as far as I know. How to find the finest net to catch convex polygons. So here's the setting. You have a square, and you are given K lines. And what you want to do is arrange those lines on top of the square so that you catch particular convex polygons that are, say, dropped into this environment. Now, let me explain this. Suppose you want to catch squares whose aspect ratio is 1:1. If you put, and suppose K is 4, so you have 4 lines. If you put the 4 lines in parallel, you would catch this and anything larger than this. If you put the 4 lines in a grid, then this, which is the same size as this, could fall right through the net and you'd never catch it. So I believe if you're searching for squares and you have 4 lines, that this is better than this. And so I'm asking, you want to achieve the smallest scaling of the given polygon, in this case a square, that will always be caught, no matter how it's oriented and dropped. So again, using these same 2 possibilities for 4 lines, suppose you're trying to catch rectangles that have an aspect ratio of 3:1. Then this scheme could allow this rectangle to fall through if it's oriented vertically. But over here, it would always catch it. So this net is better for the 3:1 rectangles, and this is better for the squares. And so the question is, if you're given K, the number of lines, what is the best net to catch a given polygon?
Joe?
Yeah.
Do the lines have to be parallel to the sides?
No.
Or can I have like things cutting diagonally across?
Right, you could have it cutting diagonally across. So I don't even know, I believe I have a proof that the square, it's best to use parallel lines.
Okay, because if I have like 2 diagonals and 2 that are, let's say they all go through the center of that square. So I have, wouldn't that catch smaller squares than 1:1?
No, I don't think so. No, I think this is the best for squares.
Okay.
But it takes some analysis, and I don't know that this is the best for 3:1 rectangles. I just wanted to show an example where this is not the best.
Right.
And yeah, once you get the diagonals, then the regions become less regular.
Yeah, exactly. So that's why I thought it would like maybe catch the squares because they don't fit through.
Right, yeah. No, so I worked pretty hard on this, and I cannot see how to solve it. And it seems to be a little different than anything else I've seen. Any other comment or question? Okay, so that's all I have. And so now I will bring up the whiteboard and ask people to pose a problem, and you click on text and you can type, or you can also draw. Let's see, I didn't take it.
Joe, could I just talk a problem, do you think?
Sure. So let's at least identify you and so
Mike
who is this?
Mike Patterson.
Oh, Mike Patterson. Okay.
Speaking from Warwick. Okay, so can I go ahead? One
Yes,
T.
please.
One T in Patterson, please. You might
Oh,
call
excuse me.
Yeah, right. Okay, thank you. Okay, so this is, let me give you a little story. So many years ago, I had the pleasure of co-teaching a group of talented 13-year-olds with Christopher Zeeman, who is a great geometric topologist at Warwick. And he was telling them about the Platonic solids and showing that there were only 5 of them. So one common definition is that these are polyhedra with all faces are regular argons and all vertices are of degree S for some R and S. And then simple analysis with Euler characteristic shows the only possibilities are the tetrahedron 3,3, the cube 4,3, the octahedron 3,4, and the icosahedron 3,5. But I was sitting there listening to him, and I noticed that he actually omitted to say that the polyhedra had to be convex.
Mm.
And so as I listened, I pondered the case 3,6, where there are 3 equilateral triangles meeting at each vertex. And of course, by Euler, the characteristic in this case has to be 0. But to this day, I don't know whether or not a torus can be built with this structure.
Mm.
So fairly easy progress I found was like I can actually build a torus. I can make a triangulated torus, which is flat at each vertex. That is, the angles of the triangles add up to 2 pi around every vertex. But I don't know whether this could be done with equilateral triangles. And if it could, this would naturally be called Plato's torus. So that's the question.
Of course, there is something called the flat torus, which plays a role in topology. Yes. Jeff?
So this
So I heard flat torus. So there are results about combinatorics of Platonic toroidal maps. And if I remember the results correctly, they're all quotients of the regular planar tilings by squares or triangles or hexagons. And there's even some results about geometric realizations as polyhedra, but not with regular polygonal facets, as far as I know.
So, Joe, this is a question that I asked on my blog many years ago, and I've also worked on with Tomohiro Tachi. It is possible with...
Excuse me, could you identify who's speaking? For some reason,
David Epstein.
Hi, David.
So it is possible with equilateral triangles meeting 3 at a vertex to make structures that look locally like tori. They they bend around rigidly in 3 dimensions, but those structures are rigid and they come around and don't meet up exactly, as far as we can tell. There are many different ways of doing it.
Yes.
And all the ones that we've calculated don't make a completely even 360-degree circle. They come around at an irrational total angle.
Yeah. Something that would be really nice, I think, is you can make sort of cylinders out of these triangles. So you've got something like nanotubes, and there are lots of degrees of freedom. And I was thinking, wouldn't it be great to make a robot arm, which you just was made out of nanotubes of equilateral triangles, and then you deform them a little bit at the base, and they wiggle around in all kinds of beautiful ways.
Mm.
My experience with playing with these regular equilateral triangle structures is they are not flexible. They lock into a position, and there might be a little bit of flexibility at the ends where you haven't connected it off, but it's not flexible in the middle.
Okay.
Cool. Any other comments on Mike's question?
I included in chat the link to David's blog post about this, which I think includes the history of the problem.
Thank you, Art.
It goes back to Nick Holloway in 1997, at least.
1997? I was thinking of that in early 70s.
Okay.
Okay.
Okay, anyone else want to suggest a problem?
I have a problem.
Yeah, just take it away. Don, you want the whiteboard?
No, actually, I have a document camera. I'll switch to that in a second. So I got a 3D printer, and so like any good computational geometer, I let's see if this works. I started printing some Voronoi diagrams. So so I had this idea. It's a very simple idea because I didn't really want to learn a new CAD software, that I would just generate shapes by taking Voronoi cells. And this is kind of nice because it's a very clean way to express a shape. You just give a bunch of points and you say which subset of points are going to be your shape. So this is the union of 4 Voronoi cells. This is the union of 4 other ones. They're actually, the cube itself is not artificial. Actually, there were other points reflected around the faces so that the cube kind of is realized also as a union of Voronoi cells. And so I started making these more complicated ones. And let's see which one I want to show first. And the goal, actually the vision was, I was thinking about this amazingly satisfying experience that most people have had where you break a pencil and you put it back together and it fits. Hopefully you know what I mean. And so I just took points in the cube, and I took half the Voronoi cells and the other half split along a plane, so I knew that they would fit together. But when they fit together, of course, they don't fit very nicely because the print is not perfect, right? And so with a little hackery, you know, I could shrink the Voronoi cells a little bit so they fit together more nicely. But this is totally faked. So what I did was I just added points along the Delaunay edges to move the faces orthogonally. And so what I think would be nicer would be to change just the weights and have the power diagram. So it turns out this is kind of a funny problem even in 2D, and I think I can express it. So here's the idea. Let me pull out a picture. In 2D, I've got some points, and they're red and blue. And my goal, actually, let me do an even smaller example. Say it's just 1. My goal is to change the weights of the points. And I would like to create a uniform amount of space between the red cells and the blue cells. So uniform in the sense that I want to shift, let's say I want to shrink the red one by changing the weights. And I would like it to be kind of like in a straight skeleton where it's just the orthogonal distance. Is this clear? The orthogonal distance between the old facet and the new one is uniform everywhere around. So in this case, you can do it. And there's some other cases, like I think in this case you can do it. So when I wrote the problem down this morning, I realized a bunch of stuff about it. So it seems that the topology of the interface between the red and the blue really matters. It seems that if the edges that you care about form a tree, then it looks like you can do it. But I think if you have even this case, which seemed quite easy, where the red cells make a nice simple polygon, I think if these points are in general position, I think you can't assign the weights to make this work. So let me just try to state the problem a little more carefully. You want to do, you've got your red points and your blue points. Let's just do it in the plane. And the goal is to assign weights. And you can assign the weights. Is this mirrored for you all or just for me?
Oh, it's working. We can read it.
I want to assign weights. So, and such that the power diagram, right, this kind of weighted, one variant of a weighted Voronoi diagram, moves, and I'm going to have to put this in quotes here, moves all the facets orthogonally by the same amount. Now, some facets can get squeezed out, and that's kind of okay, orthogonally by a fixed amount. And obviously this fixed amount has to be less than the length of the shortest edge or something. So this kind of, if you were to just try to solve for the weights, it turns out you can write this as a linear system. That linear system is just the incidence matrix, the signed incidence matrix of the red-blue edges in the Delaunay triangulation. So some of these results start to look a lot like Maxwell-Cremona or some other kind of classic computational geometry questions. But my other question, I guess, is if you can't do it, so the question is, when can you do it? And like what conditions might you put on the red and the blue points or the union of their Voronoi cells so that you can solve this? And if you can't solve it, what can you do instead? Because I still want to print these things.
Very nice.
Yeah, so here's another example. This was the one that this was actually a part of a three-way joint. It looks very regular, but this is Voronoi cells. But I was trying to, it just got stuck. It didn't fit in the gap, and then it broke when I tried to force it. All right. Questions?
Yeah.
I have a question, Don. Oh, sorry.
Yeah.
Go ahead. So are you primarily interested in the case where in 2D the red-blue interface is an open curve, or in 3D where it's an open surface like in your
Yeah.
examples?
So one advantage of talking about geometric models as just subsets of Voronoi cells is that it's a volume. It's clearly a volume. You don't have any of the printing issues about being watertight. And also it's easy to check connectivity. So yeah, it seems those at least seem to be the most interesting cases for me. But more generally, I mean, you can, if you have even just polygons with holes in the plane, you can really get, you can make it even harder. But even this example that I've drawn here, I'm pretty sure you can't do it. I think that the cycle is enough to end it. I think because the sum of the alternating sum of distances along this cycle would have to be 0.
Yeah.
Which is not something that's going to happen generically.
So Don?
Yeah.
This is Erin Chambers. Is your conjecture that the simply connected or the tree in 2D is necessary and sufficient, or do you know of any examples that are non-trivial, topologically non-trivial, where you can still solve this?
Yeah, so the problem is that in attempting to write it down this morning, I figured out a lot of stuff. So it's less open than it was an hour ago, 2 hours ago. But so I'm pretty sure that if you have these cycles and the points are in general position, you can't do it. So the question is, how do you fix it? So how close can you get? And you massage the points or make this minimal change so that you get this kind of even, either even or close to even gap between the interface between the reds and the blues. Yeah, so once I wrote it all down and saw that there was just a linear system in here that you just have to solve. But like I said, you can see that this case it's somehow it depends on the fact that it doesn't wrap all the way around. But other than that, I don't know. Or I guess the other question is there another better way of getting a clean interface, or like a clean gap? Because also, it's not just so that they fit better, but if you were going to make parts in multiple pieces and you wanted, say, an even amount of glue, you need a little space for glue or glue to expand, then you'd want it to be kind of, I think, pretty uniform around on the surface.
Hey, Don, this is Satya and David. Just a quick question, man. Would you be willing to like add a new blue point to kill the cycle to make it into a tree, so then it would work then?
So I'm not sure. In this case, I don't know how to do it. I mean, add a new blue point somewhere, like turn the red point blue,
or even add a new Voronoi vertex.
Yeah, so that's one idea that I was thinking of. One other possibility is you have a kind of keystone where you kind of maybe drop 2 points, right, one on either side, and you allow one edge to be, you don't enforce that one edge moves.
I see.
So you have one small one that can go real bad, that can break a cycle. But I don't know how to just add one blue point to break these kind of cycles.
Okay, great, thank you.
Anyone else have a comment? Okay, thank you very much, Don. Anyone else want to volunteer to discuss a problem?
Well, Joe, can I jump in?
Yeah, please.
These are two problems related to each other that I've been thinking about for a little bit. One is there are these 261 unfoldings of the 4D cube, and they all sit in these nice boxes. So if you add the lengths and the width and the height of the 3D, like the nicest 3D Amazon box you want to ship these cubes into, the sum of the three sides have to add up to 10. And this is true in general. If you want to unfold cubes, they always fit into these 3n minus 2 summed boxes. So for n equals 4, 3 times 4 is 12 minus 2 is 10. So you get these 10-sided things. So a 6, 2, 2, 5, 3, 2, 4, 4, 2, and a 4, 3, 3 are the only ones. And the last condition is that the size of the dimensions have to be at least 2 in this partition. So you're partitioning 10 into 4 parts, and into 3 parts. The question is, out of these 261, what's the distribution of that number into these 4 boxes? And in general, there's a way to, this is true for any dimension. You could always unfold cubes into nice nets, and then there are these boxes that exist based on simple integer partition. And so what's the distribution? I just got an email a few days ago by Takashi, who was able to compute the next number of unfoldings. He said it's 9,694 unfoldings of the 5 cube into 4D. And then there are only like a handful of those boxes, right? The integer partition is not too many, but then you have this 9,000 plus things, and yet they only fit into a few things. So do they, most of them end up into like these longer, skinnier boxes? Are they kind of cubey boxes? And even like a rough idea, I'd like to know. So that's one thing. I hope that question makes sense.
Yeah, I think it does. And certainly the 261, there are various pieces of software out there that calculate these, so we can easily get the distribution for that. But
yeah, I don't even know if it's done. Maybe people have already figured this out.
Done that. But even for the 9,000, I don't. You could ask him to compute the distribution for you. It would be interesting to know if it's generally long and skinny, or are they all kind of clustered.
Yeah, that's exactly what I was curious about.
Yeah,
Takashi is here.
Yeah, I tried.
Oh, yeah.
You tried already. Great.
Okay, good. So there's some forward movement of interest. So the vector is pointing in the right direction of interest. That's good.
So what did you find, Takashi?
Yeah, I just try to check the distribution.
Give him another 10 minutes.
I have a question before you jump in. So is it known that in the higher dimensional cubes, they also get this kind of integer partition property in the boxes that they fit into? Is that pretty straightforward?
Yeah, that was my CCCG paper. So thanks for reading it, Don. That really says a lot about our friendship. But so we know that you could always unfold path. So given a box, I could always unfold a path of a cube that fits in a box. So all the boxes are actually there's always something in boxes.
Yeah.
Right. So we have the fact that they have to fit into these boxes, and there's always something in these boxes. There's never a box that's empty. But in terms of which boxes kind of pick up a lot of stuff, I just don't know anything about it. And then the second question, which is related to unfolding, is simply, Takashi has this beautiful result in 2011 CCCG that he showed that every unfolding of the Platonic solids yields a net. Every edge unfolding of the Platonic solids yields a net. And they have these enumerated results along with it. And so my question is just the analog for higher dimensions. So for regular polytopes, instead of cutting along edges, you cut along codimension 3, which are called ridges, and then you can unfold them. So for regular polytopes, we could show it true for the simplices, and then we could show it for the cubes, the CCCG. But there's only one last regular polytope that exists in all dimensions, which is the dual to the cube, which is the octahedron. And so I was able to kind of figure it out for the 4D case that unfolds into 3D, but cubes are tiled, the faces of cubes are other smaller cubes. So things are really pretty when you unfold them into n-1 dimensions because cubes tile space. But tetrahedra or n simplices don't tile n space. So for the 2D case, it's really pretty because you have these equilateral triangles tiling things, but then things get really ugly and you have to keep track of a lot of things. And so this is one last punchline left over for 5D and up, which is this octahedron. So I'd love to figure it out. I made a little bit of progress, but not enough to finish it up. And then the second thing is in the 4D case, there are 3 exceptional other objects that come up, the 24 cell, the 600 cell, and the 120 cell. And those are the only 3 exceptional ones. So that could be a computational argument that one can be made to check that. And then whereas I think for the simplest octahedron, one needs kind of a geometric argument to make sense of that. That's a little prettier. And in order to check them, I think you don't actually need to know what the nets look like. You just need to find paths. As long as all your paths unfold nicely, because the dual of all of these guys are trees that you're unfolding, right? So if there's ever a place of intersection, you just need to find, the 2 vertices of intersection and say there's a path. So if all the paths unfold nicely, then all the nets are going to unfold nicely. So we just need to think about the paths of these structures of unfolding. And there are a lot of these little packetings that happen for some of these creatures. So we have to be careful how you spin around them. So that sounds really interesting to me. I'm really curious about the geometric weaponry needed for that. So,
yeah, I think this should be solved. The community should solve it.
Yeah, exactly. Thank you.
Any more comments?
This is Anna Lubu. So this is a question that maybe came up from your talk, Satyan. But thinking about the opposite of unfolding higher dimensional cubes, which is to take a collection of lower dimensional cubes and fold it up into a higher dimensional cube. And I believe someone also mentioned this unfolding, we could repeat it. I think maybe Joe said that.
Yeah.
So start with a higher dimensional cube, unfold it, you get some orthogonal thing, unfold that and repeat. So then what I want to ask is, given a planar collection of squares, can you fold it into a 3D structure, which you can then fold it into a 4D cube? And you might be curious, like your question, as to which boxes such things fit in.
Yeah, that's pretty. That's really cool. And in fact, you could just keep going up, right? Depending on the number of kind of tiling or structure on the plane. Oh, that's great. I think, did you have something like that, Joe? Maybe written up going the other direction?
Yeah, I did have something, but it was for tiling. In other words, you take a n-dimensional cube, you unfold it, and that can tile space. And then you unfold it, and that can tile space, and unfold it, and then you get down to the plane, and that can tile the plane. So we were not looking for everything, but we found these examples. For example, in the 261 unfoldings of the hypercube, we found several of them which tile 3 space.
I see.
For example, the most famous one, the Dali cross.
The cross, yeah.
That tiles 3 space, but it's not completely obvious that it does.
That's cool.
So I'm a little confused. If you have, even if you just have 2 cubes in 3D, like so 2 adjacent faces of the 4 cube, how can you ever unwrap that into the plane? Is that, oh, I see, never mind. Okay, you can, I'm just worried about the face between the 2. It has to go somewhere.
No. So you treat if the 2 faces are joined, you just treat it as it's not there, it's inside.
Okay.
So in other words, you treat the unfolding of a hypercube as a polycube, as we say in 3D, and then you unfold the polycube by cutting the surface, and you ignore the hidden faces.
Okay.
Well, another possibility would be to fold directly from 2D into 4D, ignoring the volumes and just looking at the 2-dimensional surfaces and the edges connecting them. So in that sense, for instance, an Euler path is a 1-dimensional unfolding of any higher dimensional thing. And we could similarly ask for 2-dimensional unfoldings of the squares of a hypercube into some connected structure in the plane.
Yeah, that's great.
Because this idea of folding a polycube and then folding that polycube into a hypercube somehow seems a little flawed to me, because then the squares between the cubes of the polycube never go upstairs into the hypercube.
Yeah.